Hello everyone, I am Vivanchala. Welcome to my YouTube channel, Space Engine. This is a series of short videos in which I will explain some concepts about the universe. As such, theory of general relativity, dark matter, and particle physics. I will upload every day, so stay tuned. I hope you enjoy. Today's topic is last stages. The last stages of a star's life produce exciting astrophysics. Every star starts by burning the most abundant nuclear fuel, hydrogen, and turning it into helium. This defines a main sequence star, of which the Sun is one example. The formal relationship is that the lifetime on the main sequence goes as the mass of the star to the minus 2.5 power, a very rapid dependence. Although there is convection in a star mixing the material, the end of a star's life does not denote the end of the hydrogen. There's always some hydrogen left over unused. But in general, the star will form two distinct parts. The loss of energy support in the center as hydrogen fusion stops leads to the inner parts of the star collapsing. Meanwhile, energy is generated from this collapsing core that drives off a diffuse envelope into space. This diffuse envelope, after the Sun leaves the main star, will read to the red giant state. Seen from afar, we do not see into the core, we see in the photosphere, and this photosphere of the Sun will then cool and become a large object, a red giant, while the diffused envelope expands and cools to the temperature of a few thousand Kelvin. The core collapses and reaches a new significantly higher temperature, close to 100 million Kelvin. At this point, helium nuclei can fuse to form carbon. However, there is still some burning in a shell of hydrogen into helium, so both processes occur in parallel, and indeed in very massive stars, a whole series of different fusion processes occur in parallel at different temperatures, increasing, moving towards the center of the star. The star reaching this new equilibrium state is once again stable, forming carbon from helium, but this fuel will not last as long as the temperature is hotter, the burning rate is higher, and the lifetime is shorter as a red giant. When the energy source is removed by the end of the helium turning into hydrogen and carbon, once again the star must find a new configuration. When the red giant exhausts its fuel, the carbon-rich core must collapse. In low and intermediate mass stars, up to about twice the Sun's mass, the temperature never gets hot enough, 600 million Kelvin, for carbon to fuse into new elements, and it's the end of the process. Meanwhile, the helium and hydrogen burning shells outward from the core overcome gravity and gently blow off parts of the atmosphere star into space. Perhaps a third of the star's total mass is lost in this way. This is why it's called planetary nebula. This ejected gas is heated by the ejection itself and glows luminously. Neutrons have no electric charge, so this matter can form nuclear densities. In other words, the entire star can take the density of an atomic nucleus but of huge mass. This neutron star collapses until it's stopped by the pressure of degeneracy of neutrons themselves. That pressure leads to the core to bounce and material heats outwards at relativistic speeds. This core collapse takes place in less than a second. The bounce phase is perhaps a millisecond, and the result of this enormous energy disposition outward is something we see as a supernova. Supernovas form in two different ways, called type 1 or type 2, although subclasses have now been defined. In a type 2 supernova, an isolated massive star dies explosively. In a type 1 supernova, the system is a binary system where the star is triggered to another where there are fairly close within, say, 100 or 1,000 times the radius of either of the stars. This is a particularly type of orbit. Most binary stars in much wider orbits, the supernovae that occur in a binary system, are particularly valuable to astronomers because of the regulated way the mass is transferred. The explosion has a very well regulated and typical amount of energy, constant between systems to within 15%. When the collapse of a giant star at the end of its life is more than 3 times the mass of the Sun, there would be no force of nature that can resist the continued collapse. Not electron degeneration, see pressure, not neutron degeneration, see pressure. In principle, the stellar remnant must continue to collapse to a state whose properties are as bizarre as any state of matter in the universe, a black hole. Thanks for watching. Please share your thoughts and ideas in the comment section below. Bye.